Hello there, wonderful people. In the last video, I solved the linear differential equation for a simple harmonic oscillator, and I received a result in the following kind of general form, which I'm going to write in this way for this video. C1 cosine x plus C2 sine x. This was the form of my solution in the last video, and I claimed that I would be able to rewrite this in either a singular cosine function, a cosine x plus phi with some phase shift, and I could write it as or I could write it as a singular sine function, a sine x plus phi. Right? So what would be the values for our A, which I'll just say it now, this would be our total amplitude, and phi, which would be our phase shift in order to create this equality, right? Or in other words, how do I combine uh, this cosine function and this sine function together into a singular cosine and sine function? So being able to combine cosine and sine waves into this form, right, where you can immediately recognize the amplitude of your wave and the phase shift of your wave is, a very important skill in physics, and it comes up all the time in a bunch of different areas. So this is a really important and useful transformation that we should feel very comfortable uh, about using. So let's go ahead and discuss how we would actually go about and do this. And one really nice way, right, if we look over here at our right hand side, is we can kind of derive both this red and this blue by considering Euler's formula. In other words, what I suggest is that if I write out a times e to the I times x plus phi, we know that this is going to be equal to a times cosine of x plus phi plus I times sine of x plus phi. And from this, we can see if I take the real part of this, right, I'm going to be left with a times cosine phi. And if I take just the imaginary part of this, I'm going to be left with a times sine x plus phi, right? And so I can use manipulations in Euler's formula, right? Use Euler's formula, and then at the end, just take the real part or just take the imaginary part, depending on whether I'm interested in investigating a cosine x plus phi or a sine of x plus phi, right? So Euler's formula is going to be really, really useful here. In other words, I'm suggesting that we can rewrite this top equation here, right, this top relation here, as we're either taking the real part or the imaginary part of a times e to the ix plus phi. So now all we really have to do is we have to manipulate this right-hand side, pick, do I want to look at a cosine wave or do I want to look at a sine wave? And then from there, if we manipulate this right side in the correct way, we'll be able to very easily see how this A and how this phi are dependent on C1 and C2, right? And that's a beautiful thing. So let's go ahead and look a little bit more about this right-hand side. And since we've written this out in Euler's formula, it's really easy to actually simplify this out. Watch this. So if I have a times e to the I times x plus phi, I can simply write this, right? It's sum in the exponents, so I can just write this out as e times e to the ix, e to the I phi, right? We all feel good about that step. Then this is just going to be a times cosine x plus I sine x. And of course, this is now just times this guy, which is going to be cosine phi plus I sine phi. right? I just use Euler's formula on both of these two guys. They're multiplied together, and of course, these are multiplied together. Hopefully we feel absolutely fantastic about that. I'm just using Euler's formula. All right, so from here, I'm just going to go and distribute this whole thing out. So we get A times cos x cos phi plus I sine x cos phi plus I times cos x sine phi. Remember, for this last term, I times I is -1, so minus sine x sine phi. Just for organizational purposes, let's go ahead and group this into the real and imaginary parts. So we have A cos x cos phi minus sine x sine phi. Put this in parentheses to indicate that this is our real portion, plus I times sine x cos phi plus cos x sine phi. Fantastic. So I'm going to go ahead and pause here, and let's just take a moment to appreciate what we've done here. So we had that a times e to the I times x plus phi. We had this argument x plus phi, our given angle, and they were stuck together. They were trapped together in these cosine and in these sine functions here. And by exploring this, right, by rewriting it in this way, we've successfully we've separated out the x and the phi. So they're each in their own cosine and sine functions. And that's really, really powerful, right? Because we don't really want to compare, right? If I'm trying to identify information about C1 and C2, I don't want to compare apples, right? This cosine x and sine x to oranges, x plus phi in here. No, no, no. We want to compare apples to apples, right? We want to compare these guys effectively, where I have cosine x, and I have sine x, sine x. You see what I'm saying? Because we're never going to get anywhere if we try to compare x plus phi as our input to x, for example, or x, right? That's not going to happen. So this is a very useful transformation in order to solve this problem. And remember that based on what we discussed earlier, if I take the real part of ae to the I x plus phi, right, then this is going to give me my result for my cosine wave. And if I take the imaginary part of ae to the I times x plus phi, this is going to give me the result for my sinusoidal wave. So really it boils down to a question of, what do we prefer? What do we want to combine our cosine and sine wave into? Do we want to combine it into one singular cosine wave, or do we want to combine it into one singular sine wave? So I'll go ahead and start by taking the real part. So let's explore this. So if I choose to take the real part of this equation here, I'll be left with a times cosine x cosine phi minus sine x sine phi, right? So again, I've chosen to go down this route. I'm solving for a and I'm solving for phi such that c1 cos x plus c2 sine x equals a cosine x plus phi. That's the choice that I've made. Sound good? If that sounds excellent, then from here, we know that this quantity will equal c1 cosine x plus c2 sine x. And let me go ahead and move this over a little bit. And now I really want to make sure that we feel absolutely clear about this. So I'm going to rewrite this one more time. in a very suggestive way. A times cosine phi times cosine x minus A times sine phi times sine x equals C1 cosine x plus C2 sine x. Or maybe, actually, I'll even change this color here, right? Just so that we really truly see the emphasis on the point that I'm making here. Right? That I can compare, because A and cosine phi, we know that A is just the amplitude and cosine phi is going to be my ultimate phase shift. This is just another constant times cosine x, and this equals some constant times cosine x. And we have some constant times sine x is equal to some constant times sine x. Really, this is two separate equations encoded in one. And just to make this absolutely clear, this idea absolutely clear, the key is that the cosine x and the sine x functions are linearly independent, right? What do I mean by this? Well, again, the condition for linear independence is that if I have alpha times some function of x, f1, plus beta times some function of x, f2, this equals 0 only for alpha and beta equal to 0, right? Or in other words, there's no way to linearly combine or create a linear combination of f1 and f2 such that they sum equal to 0. Thus, they are linearly independent functions, right? And this language can be more generalized for any vector, but since we're talking about functions, let's not make this confusing and just stick to talking about functions. But again, it's very common sense, right? So like if I had a times x plus b times x cubed, and this was equal to 5x plus 7x cubed, I think anyone could tell me in this situation that a is equal to 5 and b is equal to 7, right? Because what you're implicitly doing is you're saying ax equals 5x and bx cubed equals 7x cubed. In your mind, you're implicitly breaking it down into two equations, right? What I'm saying is that that is the exact same logic that we're going to use up here. So please don't get confused at all when I do the following, right? I'm going to go ahead and I'm going to break this down. I have a times cosine phi times cosine x, right? Compare my apples to apples. This is going to equal C1 times cosine x. And next, I'm going to do the exact same thing over here. I have minus a times sine phi times sine x, and this is equal to C2 times sine x. And look at this, right? Now we can immediately cancel out cosine x and sine x. And that's going to leave us with the following system of equations. A cosine phi equals C1, and minus a sine phi equals C2. We feel equally fine that a sine phi is equal to minus C2. Yes? Great. Now isn't this interesting? We could just solve this, right? We could solve for a and we could solve for phi from here very easily. But I want us to really appreciate this statement here. because this tells us a very important fact, and I can kind of draw a really nice picture now to see how A, phi, C1, and C2 all relate to each other. And we've derived this fact, right? So I'm just going to have some xy plane. The significance of the axes is irrelevant. I'm just using this to graphically represent some ideas. So in polar coordinates, I could go ahead and draw out some point with a radial distance a from the origin, and it has some angle phi. And of course, this a we could break down. That's not a very straight line. We could break down into its vertical and horizontal components. And of course, if I asked you for the vertical component, we could just say immediately, oh yeah, trigonometry, this is a sine phi, and this horizontal component down here is just a times cosine phi. Great. But look, what did these equations tell us? They tell us that a sine phi is equal to minus c2. And they tell us that a cosine phi is equal to c1. Oh my gosh, this is really neat. Because in other words, right, let's look at this triangle. I'm just going to go ahead and eliminate this kind of intermediate step here, right, and pretend like we're looking at this problem from scratch. I have some C1 and C2, and I want to combine them into a single cosine wave with some amplitude A and phase shift phi. This picture here immediately tells us how A, phi, C1, and C2 are all related to each other. In other words, if we just always have this picture in our mind, we can immediately come up with these equations here on the left, right? And so just with this little visual tool here, you can immediately tell me if I were to ask you what A is, right? This is a triangle. Let's use Pythagorean's theorem. A squared equals C1 squared plus minus C2 squared. And of course, this leads us to A equals plus or minus the square root of C1 squared plus C2 squared, right? And of course, A is just some positive radial distance. It's just the hypotenuse of our triangle, so we just take the positive answer. Perfectly natural. Okay, so what's phi? Well, we can see here that in terms of C1 and C2, if I take the tangent of my angle phi, this is going to be equal to the opposite, minus C2, right, over my adjacent, C1. And therefore, phi is equal to the inverse tangent of minus C2 over C1. And of course, you could go ahead and define this in terms of cotangent if you want, and take the adjacent over the hypotenuse, or whatever feels appropriate. But we very clearly defined relations between A and C1 and C2, and phi and C1 and C2, which was the goal of the problem. That was our objective. And just to make sure, in case you don't, in case you are skeptical, although you shouldn't be skeptical of this triangle that we've drawn, this is 100% rigorous and valid. It's just a very geometrical way of looking at this problem. Let's go ahead and solve this system of equations analytically, just to confirm this. I could, of course, divide through these equations, and I would be left with cosine phi over sine phi is equal to minus C1 over C2. Of course, cosine phi over sine phi is cotangent. Let's go ahead and get the tangent answer. Okay, so I'm gonna go just flip this around and say sine phi over cosine phi equals minus C2 over C1. And of course, this tells me that tangent phi equals minus C2 over C1. And of course, so we just have phi equals the inverse tangent of minus C2 over C1. Right. And of course, we can see our results are identical. Okay. And we could also very easily solve for A if we just do the following. I'm going to go ahead and take this top equation here and square it, and I'll take this bottom equation here and square it as well. And then I'm going to add the two together. Where does that get us? I just get a squared cosine squared phi, right? I squared this top equation. And next I'm going to add it to, I squared the bottom equation, a squared sine squared phi. And this, of course, is going to equal c1 squared plus c2 squared. I'll write this more explicitly as a squared times cosine squared phi plus sine squared phi. And this equals c1 squared plus c2 squared. This, of course, just equals 1, right? And if you don't know why cosine squared plus sine squared equals 1, let me just draw out a very quick picture in 5 seconds. Perfectly easy. I have some radius 1, right? This is on like the unit circle, but I have some radial distance 1. I very easily break it into, oh, and it's at some angle phi, of course. So I can easily break this into cosine phi and sine phi. And of course, by Pythagorean's theorem, cosine squared plus sine squared equals 1 squared, which is just equal to 1. So it's probably one of the easiest, but also most important trigonometric identities. And so we're left with A equals plus or minus square root C1 squared plus C2 squared. And again, we choose to take the positive answer. And bingo. Of course, this goes and it matches exactly with the form that we derived earlier. And thus, we have now confirmed that C1 cosine x plus C2 times sine x equals A, which we now know is square root of C1 squared plus C2 squared times cosine of x plus phi, which is the inverse tangent of minus C2 over C1. Just put it all together. Although I don't usually write it out in this form, right? Like this is not an equation that we memorize. We use this little picture here with our little triangle, this very nice pretty picture. We just draw it out and we immediately get A and we immediately get phi from this beautiful picture. And that's all there is to it, right? It's really not that bad. And what I would suggest, and I'm not going to do this in this video, right? I'll leave this to you. Explore this imaginary route, okay? Explore this. I'll go ahead and show the equation that I was left with. We could try taking the imaginary part and just go through and do the exact same thing I did before, right? Equate the imaginary part here to C1 cosine x plus C2 sine x. Go ahead and compare your apples to apples, right? Write out two equations, just like I did. Come up with these two key equations. See if you can come up with a picture to show what those equations represent, right? And then solve those equations in order to come up with equations for your amplitude and for your phase shift. Anyways, I hope this video was really nice and helpful in teaching us how to combine sine and cosine waves into a single unified wave with a given amplitude and phase shift. This is a very critical skill in physics, and it comes up all the time. So I hope you enjoyed that video, and thank you so much for watching.